continue straight from last video where we calculate the reinforcement in the y direction, secondary direction on a long span. Now this video explains the calculation of transverse shears. We need to make sure that we have done the bending check, we have done the deflection check, and we need to do the shear check for this slab. Now at the face of the interior supports, if I can show it to you here, our examples, we have drawn these kind of figures where it says that at the face of interior supports, at here along this one, we have a very high shear, design shear. So the simplified method of flexure analysis given in AS3600 will be used to calculate the design shear force. So it's basically the shear force diagram. So if you go to the clause 6.10.2.4 on page number 96 of AS3600, it has given you in the end span, at the face of interior supports, you have equation to calculate the transverse design shear force, that is denoted by V star, equal to 1.15 FD. I just put as a W star, and ln is L0 over 2. So you can just substitute 1.15 W star we calculated in the previous video. I think this W star we calculated 9.8 kilonewton per meters for this 1.2 dead load plus 1.5 live loads. You check the previous videos where we calculate 9.8, so we use that value times 5.05, that is the effective length. I think in our previous video in the discussions we use this 5.05 meter length, that's I take it here over 2, that's I just use this equation, so that will give me 28.5 kilonewtons. Now we need to make sure that we need to provide the fitment or not. Okay, so there is a conditions where I can take it to you here on that requirements of transverse reinforcements. Your V star value should be greater than 5 VU. So if it is V star equal to greater than 5 VUC, then we need to provide. If it is less, then we no need to provide the fitment. So we need to calculate this VUC, which is the concrete shear capacity. Now the concrete shear capacity is given in the clause 8.2.4.1. So I can write this clause 8.2.4.1 kV BV dV square root FC dash. Now kV is taken 0.15. if you turn the page over, they have give you this kV. There is an assumption here saying that your reinforcement should be greater than ASV mean. You can calculate this ASV mean and validate that assumptions. I think there is a ASV mean here. ASV mean has this one where you need to require the spacing of this one, but we assume that, look, let's say your ASV is greater than ASV mean. Now in that case we can have, let's say, 0.15. BV is the width of the slab. We are using 1 meter wide strip, so that is thousands. dV, I think if you go back to that clause again, back of couple of page here, clause 8.2.1.9, it has effective shear depth. Read these lines, that this line is telling me that your dV would be 0.2 times 190, which is your d, times 0.9 small d. I think in our previous videos we found that the depth of the slab was 190, so I substitute 190. Small d effective depth is 159. I substitute 159 here. In that case we will get this 143 millimeter as a dV. So VUC kV we substitute 0.15. Thousands is the width, and 143 dV is 143, and square root 25 the concrete compressive strength given in the question. So that is 107 kilonewton. Now capacity factors for the shear, capacity reduction factors for the shear, I can take you through to the tables where we have these where we have these tables for shear, and we are using class N let's assume class N fitment, so we have 0.75 as a capacity reduction factors. So 5 VUC, which is 0.75 times 107, which is 80 kilonewton. Please note this 80 kilonewton is far greater than 28. Well, we have some assumptions here, but still it will not going to come close to these 29 kilonewtons. It's very far. The concrete will carry all the shear force. Let me take you back to that clause again, clause 8.2.4, where we have these conditions where it says that your V star should be greater than your V star should be greater than phi u VUC. This is not a conditions here. As you can see, our phi u VUC, which is 107, the concrete will carry all the shear, so we don't need to provide any fitments. Okay, and please note we have some assumption here, but those assumptions, if you remove that, still this value will not gonna come close to this 29. So we're not going to recheck and do the detailed calculations for, let's say, kV and we find another kV and so on. But I think this is valid assumptions. Still it will not going to come close as I mentioned here. So we will continue. And I think we will take the one more videos where we just going to summarize everything, and we finish the design of one-way slab after the next video. Thank you.